Assalamu alaikum, dear students. We're back with another video lesson. In the previous lesson, we talked about longitudinal waves and transverse waves, or in another way, of course, we did talk about mechanical waves and electromagnetic waves as well. We said mechanical waves need a medium to travel, let's say, or need particles, a medium to travel through, but electromagnetic waves, they don't need a medium to travel through. And normally, electromagnetic waves are way faster than mechanical waves, let's say. And of course, we did talk about a lot of differences. And of course, then after that, we talked about longitudinal waves and transverse waves. We said in transverse waves, the particle of the medium, of course, when the wave is traveling, the particle of the medium would vibrate at right angle to the direction of wave travel. On the other hand, for longitudinal waves, of course, the particles were vibrating parallel to the direction of wave travel. Okay, today, and of course we stopped at this point here. Today we'll talk about period, frequency, and wave speed of a wave, of course. So let's start with a period. Of course, previously we talked about period. So period of a wave would be the time it takes for one complete oscillation or for one complete wave, let's say. Or some other times you can say the time it takes for one vibration. That would be a period here. And of course, period is measured in seconds. Okay, and then of course we have another definition, let's say, that we have is wavelength. How do we define a wavelength? Of course, we have different, or you can have different definitions for the wavelength, but I'll give you a very simple definition. We can say wavelength is, let's say, the distance between one point on a wave to the same exact point on the other wave, let's say. And all this doesn't mean anything or doesn't make any sense if I don't draw for you. Okay, so let's draw a wave and talk about each one of these, of course. Okay, so the first thing, let's start with, let's say that we have a wave, okay? All right. So let's say this is a wave, and of course this is a transverse wave, yeah? We've said that transverse wave, or in transverse waves, the particle of the medium would oscillate at right angle or perpendicular to the direction of wave travel. So the wave travel in this direction, but the particle moved back and, let's say, up and down, of course, in this direction. So this particle will be moving upward, and of course later on this particle will be moving downward, let's say. Or when the wave passes, this particle would move up and down perpendicular to the direction of wave travel. Okay, now we did talk about the period. So basically, period, the time it takes for one complete oscillation. So how much or how long is one complete oscillation? Let's say the time. This is, let's say, if this is a wave that is, for example, transferring through the medium. This is basically one complete wave, yeah? And of course, we did talk about this. Let's say if this is part of the wave, and if let's say this is the other part of the wave. If I just cut and bring this part here, let's say, bring this part here, then of course, you will get something like a circle, and that is, of course, the time it takes for one complete oscillation or one complete wave. That is basically called what? Called a period. And of course, period is measured in seconds. So the time it takes for the wave from this point to this, that is basically, we can call a period. Okay, now that is for the period. What about for the wavelength, yeah? Now, in terms of the wavelength, okay, that is basically the length of a wave, yeah? But what is the length of the wave? So we can say, basically, the distance between two consecutive crests. If you remember before, we call this one crest, yeah? And of course, we call this one trough, right? And of course, another crest here. All right, so the distance between two consecutive crests, or you can say two consecutive trough, is basically one wavelength. Now, there is a better definition for this. We can say the distance between one point in a wave to the same exact point on the next wave, yeah? So, for example, if we take a point here, let's call it point A, and this is point B. Point B is exactly the same point, but on the next wave. That is, it can be called one wavelength. Why this one is more general? Because then what about a point, for example, let's say if we have a point, let's choose a different color. If we have a point, let's say at this point here, okay? Now this is neither crest nor trough, yeah? So what would be the one wavelength for this? So remember, at this point here, let's call this point F, okay? And this point, you can see that the wave is about to move downward, yeah? Will the next point, is this the next point on the next wave, you can say, or the same point on the next wave? Of course not. Why? Because you can see here at this point, the wave is downward, the direction of the wave, let's say. Not the direction, by the way, it's just the particle movement here. But at this point here, you can see that it is upward, yeah? So of course, we cannot say this is one wavelength, yeah? You go all the way to the other end. There is another point here that is almost like very similar to this now. So this point here, can we say this is another point on the next wave or the same point on the next wave? The answer here would be yes, because you can see that at this point, you can see that the particles are about to move downward as well. So you can see here at this 2 point, or let me enlighten this one as well. Okay, so you can say at this 2 point here, we have the same exact point, but of course on the next wave. So let's summarize the definition again. The wavelength, you can say the difference between 2 consecutive crests or 2 consecutive troughs, you can say, or a more general definition would be the distance between one point on a wave to the same exact point on the next wave. That is called one wavelength. Okay, that is for the wavelength. And of course we have, by the way, wavelength is represented by this Greek letter lambda, and you do know that, yeah? And of course wavelength is measured in meter, you can say. Wavelength is measured in meter. Okay, now we have something else. We have frequency, yes? What is frequency? So we can say frequency is basically the number of vibrations per unit time. For example, let's say, how many times does this wave vibrate in 1 second? That is basically can be called frequency. So in terms of the frequency, and of course frequency would tell you the number of vibrations per second, yeah? And of course we have different waves, let's say. We have, let's say, waves with a lot of frequency, and of course other waves that has less frequency. Let's say, now for one wave we have this shape or this form of a wave in 1 second, and of course we have, let's say, another wave that happens let's say in 1 second. These two are still 1 second and 1 second. You can see that this one, there is more up and down, there is more vibration, so we can say this wave has higher frequency than this one. We can give it a names, of course. We can say A and B. So in terms of equation, how do we find the frequency? We can say frequency, of course, it is the number. Normally we say 1 over the period, or we can say frequency if like numbers of waves were given, you can say the number of waves, or sometimes you can say vibrations, all right, divided by what? Divided by the time, of course. And frequency, you already know that it is measured in hertz, yeah? It is measured in hertz. That is not hertz. Okay, frequency is measured in hertz. Okay, what is, but by the way, so this is measured in hertz. But you do know that this is equal to 1 over second, yeah? So can I say frequency is also, or can also be measured in second to the power -1? Yes, that is also fine. We can say hertz is equal to second -1 as well. Why? Because it is 1 over second, and if we take second, let's say to the top of the fraction, of course, there is this +1 becomes -1, or just second -1. Okay, so what are the things that we've learned so far? We've talked about wavelength, yeah? That is the distance, let's say, between 2 consecutive troughs or 2 consecutive crests, or the distance between one point on a wave to the same exact point on the next wave, let's say. That's one. And then after that, we talked about the period. We said period is basically the time it takes for one complete oscillation, one complete cycle, yeah? Very, very good. And of course, by the way, we can find the time using the frequencies, the period using the frequency as well. Okay, so frequency, we said it is the number of vibrations, let's say, per unit time, yeah? But so far we can say we've learned about wavelength, we've learned about the frequency, and of course we've learned about the period, which equals to 1 over the frequency as well, yeah? Frequency equal to 1 over, or number of waves divided by the period, or if number of waves were given, you can say the number of waves divided by the period. And of course we can swap this to here, so period equal to 1 over the frequency as well. This is measured in hertz, okay? Or you can say second -1. This is normally period or time is measured in second, but if we take this one, 1 over frequency, we can say hertz -1 as well. So make sure that you understand why it is -1. And by the way, what happens if we cross multiply the frequency and the period there? Take a look here. So we can say period multiplied by the frequency, you must get 1. So in terms of calculations, you can always multiply the two. If you don't get 1, that means your answer is incorrect. Go and redo your calculation. Okay, So these are, there is one more thing. What about wave speed, yeah? We do know that what is speed equal to, yeah? Speed, of course, equal to distance over the time, yeah? But what is the distance equal to here? Let me take you back to this real quick. Let's say, let's decrease the thickness here. We do know that speed equal to what? Speed equal to distance over, okay? Let's say x over the time. Okay, but you do know that this x that we have, or the displacement that we have, not the displacement, the distance that we have, you can say, of course, it is equal to what? It is equal to the wavelength. So we can say x in here is equal to the wavelength here. What is left in this case, yeah? So we can rewrite this one as 1 over t multiplied by the wavelength. But you do know that 1 over t, or 1 over period, is equal to the frequency. So we can say the speed of the wave equals to frequency times the wavelength. Wavelength times the frequency makes no difference. And speed, of course, is measured in meter per second. This is measured in hertz, and this is measured in meter. Okay. Now that is all about this so far. Okay, now, like talking about this a little bit more, we have wavelength. We said, like we've mentioned already, that it is measured in meters. So you can say the distance between two crests, one crest, this is another crest, and then, or the distance between two troughs, or the distance, let's say, between one point on a wave to the same exact point on the next wave. Okay, what about the, I didn't mention the amplitude so far. We're going to talk about the amplitude as well. The distance between two consecutive crest or trough, that would be one wavelength. You can say the distance from a crest. One thing that is very important here, the distance between, let's say we have a wave, yes? Okay, so the distance between, this is a crest, you do know that, yeah? Crest, and this is trough. We said that the distance between two consecutive crests is equal to one wavelength, yeah? What about if the distance was between a crest and the next or consecutive, like crest and trough in here? So what would be the distance here? And of course you can see that, can we say that this is half a wavelength? Yes, very, very good. If this is, for example, one complete wavelength, or there is another way actually you can do this, yeah? We know that in every, let's say, complete wavelength, all right, if I do one complete wavelength here, or one cycle of a wave, let's say, if we consider this, there are 4 amplitudes here. So 1 amplitude, 2, 3, and 4 amplitude, yeah? And of course, we did mention what is amplitude, correct? So amplitude, that would be the maximum displacement from the center of the wave, or from the rest position, or the equilibrium position. So here's 1 amplitude, this is 2. Okay, and this is 3, and of course this is 4, yeah? You can consider this. This is 1 amplitude. Now forget about this distance here. Let's just talk about the one complete wavelength here. So this is 1, 2, and this is 3, and this is 4. This 4 amplitude altogether makes 1 wavelength. So what if we start from this point all the way, let's say from one crest to the trough, yeah? Okay, to the trough in here. Of course, this is 1 amplitude, this is 2 amplitude, and of course 2 amplitude is half of, let's say, 4 amplitude. So in this case, we can say the distance between this point to this, that'll be half a wavelength, okay? So from this crest to the trough, let's say it is only half the amplitude. Okay, and then we have, we did talk about, by the way, the distance between 3 consecutive troughs or crest. What would be the answer to this? What is the distance between 3 consecutive troughs or 3 consecutive, let's say, crest? Let's say this is 1 crest, this is 2, this is 3, yeah? What is the wavelength here? This is 1 wavelength, and of course this is 2 wavelengths. So all this distance would equal to 2 wavelengths. What if we start with a trough, let's say in this case, that is 2, 1, 2, and this is 3, let's say. So 3 troughs would equal to 2 wavelengths. Okay. That was good. Okay, now what about the frequency? Okay, remember we said frequency is the number of waves, the number of vibrations, the number of oscillations per unit time. So we can say frequency equal to 1 over the period, 1 over the time, or if the number of waves were given, then of course we can say number of waves divided by the period. Let me give you an example. Let's say you're sitting by the shore and you observe the ocean water, okay? Let's say, let's use blue. all right? So you're sitting here, all right? And then you observe the water waves, let's say, that is coming to the shore. You'll notice that 20 waves, let's say, make to the shore in 5 seconds, yeah? In this case, what would be the frequency of the water waves? Remember, if the number of waves were given, we can divide by the time in order to find the frequency. So in this case, we can say number of waves, we have 20, divide by the time, that is 5 seconds. Let's say, and of course, 20 divided by 5, that is for what? 4 hertz, of course. So we can say the frequency of the ocean or water waves here would be 4 hertz, yeah? Okay, very good. And period, we did talk about this. Period is basically the time for one complete oscillation, which is measured in seconds. Period can be measured in hertz, -1 as well. Okay, now what about wave speed? Wave speed is basically equal to the displacement divided by the time which it takes, for example, to undergo that displacement, which is measured in meter per second. We did talk about this. We said that velocity here equal to delta x, that would be the displacement divided by the time. And then, of course, the displacement here would represent the wavelength, correct? So this wavelength divided by 1 over t, but 1 over t already equal to the period or the frequency, yeah? The t is the period, so 1 over t, that would be the frequency, so frequency times the wavelength. So far now, we have, you can say, 2 or 3 equations. One of them is for the period, which is 1 over the frequency, yes? And the other one you can say for the frequency equal to 1 over the period, and then we have another equation here for the speed of the wave, which equal to frequency times the wavelength. All right, now we have a few notes. Remember, some notes here. Remember, these notes are very important. It says, the speed of a mechanical wave is constant for a given medium. Now, that is very important. Regardless to the wavelength or vibration, let's say, and of course, the speed of a mechanical wave will be constant. For example, let's say, I'm talking, not me, let's say there is a group of people sitting in a room, of course. Maybe all of them are talking, like all at once. And of course, each one of them would have, like a different frequency, a different tone, a different voice, yeah? But the speed of these sound waves will all be the same. Or let's say that there is, like let's say music festival, let's say whatever, they are playing with different musical instruments. Maybe there's a piano, maybe there's a guitar, maybe there's a, flute or whatever, yeah? Each one of these instruments would have different frequency, yeah? But you will hear them all at once. Why? That is because the speed of mechanical waves will have the same speed in the same medium, regardless to their wavelength or frequency. Okay, and then the speed of a wave changes only when the waves moves, let's say, from one location, from one medium to another, or sometimes when a certain property of the medium changes, like what? Like, for example, the temperature. Now, frequency and wavelength are inversely proportional, okay? That means for a given wave, let's say, if we increase the frequency, the wavelength must decrease, remember. That is, if we're talking about a wave in a medium, yeah? Okay, or in a certain medium, let's say. Okay, changing the medium changes the wavelength and then the speed, but it will never change the frequency. Remember this, and of course you will be asked this question a lot. When a wave goes from one medium to another, for example, which one of the following will change? Well, the speed will change, let's say, or let's say which one of the following doesn't change, yeah? The speed, let's say, doesn't change, the frequency doesn't change, the wavelength doesn't change, or none of the above changes, yeah? And of course, the only thing that it doesn't change is the frequency. Do you know why? Because normally, frequency is the identity of the wave, let's say. If you're changing the frequency, that means the identity is changing. Let me give you another example related to this. We know that we have different colors of light, yeah? And of course, all the 7 colors. Now, each one of these colors have their own frequency. So what do you think will happen if you change their frequency? Let's say we have red, yeah? And of course, it has a certain frequency. But if you change this frequency, of course, it is not red anymore. So frequency is the identity of every single wave, okay? So the frequency of the wave, of a certain wave, let's say, it will never change no matter what. So you might wonder, how do we change the frequency? Well, then the frequency can only be changed by changing the source. Remember we said the frequency is the identity of the wave. So if you're willing to change the frequency, you must change the type of the wave in this case, not the type of the wave, like the let's say the source of the vibration that causes the wave. Once you change that, of course, then you will have a different frequency. Okay, so that is in short, frequency never changes for a certain wave. Okay, no matter like what happens, even if you change the medium, let's say you go from one medium to another, a denser medium to a less dense medium, it doesn't matter. Frequency never changes. It can only change by changing the source of the vibration. Okay, and then the wavelength, all right, can change by changing the medium. You do know that, for example, let's say if we talk about let's say the speed of light, yeah, you do know that when it goes from air into water or into glass, of course the speed slows down. We said the frequency doesn't change. So let's say what I mean is this: speed of light, let's say, equal to frequency times the wavelength, yeah? That is, let's say, in air. In water, of course, here, the speed of light will be slower, yeah? Or if it is, let's say, a solid, transparent solid. So speed will equal to frequency times the wavelength. If it is going to be slower, we said frequency never changes, yeah? Then it must be because of the wavelength get shorter. That is why the speed slows down or becomes less. Okay. And what else do we have? The frequencies of sound wave that are audible for human range. Of course, we'll focus on this more in the 4th chapter here. That is, or perhaps later on, the frequency of the sound that is audible or that is heard by the human ranges. It varies from 20 hertz to 20,000 hertz. Remember, this is called the audible range. Okay, now we have a question here. Says, what is the frequency or what is the frequency range of audible sound for human? And of course that is from 20 hertz to 20,000 hertz. Any frequency we can say between this range can be heard by human, even though of course as we grow older, of course this range would decrease, but we can say in general humans can hear frequencies ranging or between 20 to 20,000. Okay, now take a look at this one here. It says, if a wave travel in one medium to another medium of higher density, normally if the density is higher, remember this, if the density is higher for mechanical waves or for sound waves, let's say in general, the sound, or let's say the speed becomes faster. If it is electromagnetic waves, it slows down. Okay, and of course I'll explain this more in a bit, but for now, which of the following remains the same? Whenever it says which one remain the same, your first thinking has to be frequency, yeah? Because frequency can never change by changing the medium or the property of the medium. Sound waves from different instruments reach our ears at the same moment, even though, let's say, even when their frequencies or the frequencies of these sound waves are different. We said that within the same medium or inside in the same medium, the speed of the sound will be the same, okay? Or the speed, let's say the speed of the electromagnetic wave will be the same. So regardless to what the type of the wave is and how fast it is, within the same medium, the speed of that wave will always be the same. So it doesn't matter if it has different frequencies or not, the speed will always be the same. So why do we hear them all at once? That is because they have the same speed, which is in the same medium, of course. Now, what does the speed of a wave depends on, okay? Now, we can say, of course, there are, we can say factors that the speed of what? The speed of a wave depends on. Remember, first of all, of course, this question could be a little bit tricky, but let me simplify this for you. Now, we can say the speed of a wave depend on different factors. The first one, we'll have to know whether what is the type of the wave. Is it transverse waves or, let's say, longitudinal waves? Longitudinal waves, like sound waves, are normally way slower than transverse waves like electromagnetic waves. Yeah? So normally electromagnetic waves are way faster than longitudinal waves like sound. So of course we can say it depends on the type of the wave. That is one. Second, it depends on the properties of the medium. Okay, now here comes the confusion here. Remember this, guys. If we're talking about a mechanical waves like sound waves here, by increasing the density, the speed of sound will increase, but it is opposite if it is electromagnetic waves. If it is electromagnetic waves, by increasing the density of the medium, the wave will slow down more and more and more. But it is opposite if it is a sound wave. And the reason why sound wave, because, like in solid, by the way, the speed of sound in solid is the fastest, and in gases it is the slowest. The reason why it is the fastest in solid, that is because the particles in solid are very close to one another, of course, so this will help the sound to be transferred from one particle to the neighboring particle way quicker than compared into, let's say, or compared in gases or air. And of course, it is the slowest in gases. That is because the gas particles are very far compared to solids. But it is not the same for electromagnetic waves. Yeah. For electromagnetic waves, we can say the denser the particle, the more the energy, let's say, absorbed by the particle, and the less the energy would have, let's say, to travel through. Or in general, we can say it slows down more in, let's say, the denser the medium, the more the light slows down. And of course, you can see that light slows the most in diamond, because assuming that it is the densest. Okay. And then the next factor that we have, it is the temperature. Okay. Why the temperature? Take a look here. The reason why temperature is because when, let's say, once again, let's talk about the mechanical waves here, like sound, for example. Once we increase the temperature, let's say, of a material, whether if it is solid or gas or even air, let's say water, now this heating the object or increasing the temperature would make the particle vibrate faster. This faster vibration, of course, it would make the speed faster, let's say, even though we can say this effect, it is the most effective or the most visible in gases. Okay, now we have question 21, says, what happens to the wavelength of a wave on a string when the frequency is double? Okay, now remember this, we have a string, yeah? And then what happens when we increase or double the frequency? When we talk about a string, and of course, in order to hear the frequency or the sound of that string, that means, of course, you're normally hearing this through the air, yeah? That means if it is through the air, that means, of course, we have a certain speed or certain, let's say, speed for that wave, yeah? And of course, that wave is basically frequency times the wavelength, or vice versa, you can say. Let me write the other way around. Okay, so let me get the eraser. Okay. So here, let's just write this one this way. Let's say wavelength times frequency. It doesn't make any difference, by the way, which one you write first. It doesn't matter. Okay. Now, it says what happens to the wavelength of a wave when the frequency is doubled, yeah? Because it is the same medium, that means the speed is what? The speed is the same or is constant, yeah? That means it has the same value. So if we're going to double the frequency here, so in order to keep this answer or to this speed the same, of course, that means the wavelength must be decreased by half, okay? In another word here, for example, let's say that we have a wavelength here. If you're going to double the frequency, let's say you're going to get something like this. Yeah, so now this is double the frequency, but if you compare this, for example, here, one wavelength would be way shorter, or you can say half of this wavelength here. Okay, this is how we can say, because it is the same medium, by the way, so doubling the frequency in the same medium, that means the wavelength must be halved or decreased to half of the previous. Okay, now, question 23 says what? Two tuning forks with frequencies 256 Hz and 512 Hz are struck. Which of the sound will move faster through, will move faster through the air? Remember, since it is the same medium, and of course it is air, so that means these two, even though, or these two waves will have the same speed, even though they have different frequencies. Because remember, we said the speed of a wave will always remain the same if it is in the same medium, assuming there's no change in the medium, okay, like temperature or any other variables. Okay, and then we have some, let's say, national exam questions here. The first one says, if the frequency of a pendulum is 1 Hz, the period of the pendulum is what? Now this is very simple. How do you answer questions like this? Now remember, it says the frequency is 1, so we set that period equal to 1 over the frequency, yeah? So 1 over 1 hertz, yeah? And of course 1 over 1, that is going to be 1. 1 what? And of course that is 1 second, because the unit of period is second. Second one says the number of cycle of vibration per unit time. That is a definition basically. The number of cycles, or let's say cycle of vibrations, or the number of vibrations per unit time, that is frequency. Okay? Very good. Third one says, what happens to the wavelength of a wave on a string when the frequency is double? If the frequency is double, then the wavelength would be half. Let's change this question. What happens if the frequency is halved? Right? If the frequency is halved, so once again, speed equal to what? Wavelength times the frequency. If the frequency is halved, this is still in the air, so this one has to remain the same. Then, of course, the wavelength must increase by a factor of 2. Okay, very good. And but to answer this question, we said it before. If, let's say, the frequency is double, then, of course, the wavelength must, let's say, says what happens to the wavelength, so it decreases to half. But if the frequency is reduced to half, then the wavelength must double. Okay, now question 4 says a harmonic wave is traveling along a rope. Okay, the oscillator that generates that complete, let's say, wave completes 40 vibrations in 30 seconds. Okay, so how do we find the period, or find the period? Remember, we said if number of vibrations or waves or cycles were given, we'll say, to find the frequency, we'll say frequency equal to number of waves divided by the period. Okay, let's apply what we have said just right in here. Okay, so for this question, we'll say frequency here. All right, frequency equal to what? Number of waves, you can say, or here a vibration is given, yeah? Or the, yes, vibration. So we can say number of vibrations. Number of vibrations per what? Per time, or per unit time. So we have 40 vibrations divided by 30 seconds, yeah? But by the way, this one is a little bit tricky here. Okay, so 40 in this, and of course we'll get 1.33, I guess, okay? You can double check with a calculator. You might just choose this one right away, but not so fast. The question wants what? It says find the period. What you have found is the frequency, not the period. So of course you're not going to choose this one, otherwise you're going to lose 2 marks very easily. So now after you found the frequency, how do you find the period here? So finding the period, okay, so period equal to what? Period equal to 1 over the frequency. So 1 over 1.33, and of course then you will get 0.75 seconds, okay? And that is the correct answer over there. Okay, now question 5 says 3 sound sources of frequencies. Let's say the frequency of the first source is 256 hertz, the frequency of the second one is 400 hertz, and the frequency of the third one is 512 hertz, yeah? Which of the sounds will move faster through the air? You might just take a look at the numbers and say this is the biggest, and okay, so this one will move the fastest in the air. No. The question says in the air. That means all of these waves are moving through, or let's say passing through the air, yeah? If they are passing through the air, where's the question here? Through the air, we said the speed of sound in the same medium will always be the same. So what can we say about the speed of all these different frequencies? They must have the same speed, otherwise it would not be the same medium. Okay, so all have the same speed. Can we say the first source is the fastest? No. The second is the fastest? No. The third one is the fastest? No. Because it is, or all these frequencies are in the same medium, they all have the same speed. Let's just assume or pretend that one of these waves is for the guitar, one of them is for the piano, the other one is for, let's say, for violin, yeah? So each one of these can be struck, and because it is the same medium, you'll hear them all at once or at the same time. So none of them is faster than the other one if struck all at once. Okay, now for question 6 here, it says, what happens to the wave speed in a vibrating rope when the frequency is double? That is, watch this, it could be very tricky, yeah? Normally when you say, or you might just fall for this, it says what happens to the speed of a wave? So speed of a wave, we know that equals to frequency times the wavelength, true? So if the frequency is doubled, you might just say the speed must be doubled, yeah? But that is not the case. Remember, we have a vibrating rope. That means the same medium. So if the frequency is doubled, remember, if the frequency is doubled, that means the wavelength must be halved in here, okay? So that these two will cancel one another out. You'll get the speed of the, let's say, the vibration will always be constant because it is the same medium. So once again, if the frequency is doubled, the speed is the same, so the wavelength here is going to be half. So let's take a look at the choices here. It says becomes half, frequency, so what happens to the wave speed, yeah? So we said wave speed remains the same. The question is not about the wavelength, but we do know that the wavelength will become half because the frequency is doubled, the speed is the same. So let's see which one of the option is this. It says B remains the same. That is the correct one, but of course you gotta keep like reading all the options. Becomes doubled? No. Becomes 4 times of the let's say inertial volume? No, these are incorrect. The correct one remains the same because it is the same medium. It's just one rope or still in the same medium. Okay, now question 7 says, what happens to the wavelength of a wave on a string when the frequency is doubled? And of course, what happens to the speed of the wave, yeah? So, what happens to the wavelength? Now that is almost very similar to the previous one, except that there is one extra part here. It says, what happens to the wavelength, yeah, when the frequency is doubled, and what happens to the speed? We said that the speed remains constant, yeah? I don't know why, I think I've been writing C for that. That'll be incorrect, by the way. So please don't mind what I've wrote before. So it has to be V for speed, yeah? That is frequency times the wavelength, okay. So by the way, because these are the waves that we were talking about, these are not light waves. So we normally don't use C if it is not light. If it is light, then we use C. So if I used C previously, please disregard that and then just assume that I've used V only, okay? So make sure that it is V, because normally we use C for speed of light. I don't know how I didn't notice that. But anyway, so you know what it is. So if, by the way, we said this speed is going to stay the same, yeah? All right, that is the same. Okay, so if the frequency is doubled, then of course the wavelength has to be halved, yeah? So what happens to the wavelength? It will decrease to half, all right? But then the speed will always stay the same. So let's take a look at the options and see which one is correct. The wavelength is halved and the speed is doubled. This is incorrect because the speed must stay the same, yeah? This one says the speed is doubled, so this one is incorrect. Speed remains the same, so it has to be one of the two. Wavelength is halved, wavelength is doubled. This is the correct answer, which the wavelength is halved and the speed remains the same. Okay. Now, sample problem here, okay? It says a vibrating string with a frequency of 264 hertz, assuming that the speed of sound in air is 343 meters per second, find the wavelength of the sound waves produced by the string. These are very easy ones, just the application of the equation, and that's all. Yeah? So we do know that it says, find what? Find the wavelength of the sound, yeah? So we do know that speed equal to frequency times wavelength. Wavelength times frequency makes no difference. We want the wavelength, yeah? So wavelength equal to speed of the wave divided by the frequency. Speed of the wave is 343 meters per second. And of course, the frequency is 264 hertz. And of course, the answer to this equal to 1.3 meter. Okay. Take a look at the this question here. It says the speed of all electromagnetic waves in empty space is basically 3 times 10 to the power 8 meters per second. Okay? Calculate the wavelength of electromagnetic waves emitted at the following frequencies. So we have a frequency like this. Now at this point, since it is electromagnetic waves, I can use this equation. I can use C for speed, by the way. We can use C for the speed of electromagnetic waves, which equals to wavelength times frequency. All right. By the way, I can use V equal to wavelength times frequency as well, but like I've mentioned earlier, this is most common when it comes to speed of light or electromagnetic waves, okay? And then this is for speed of other waves that are less, or let's say slower than the speed of light, okay? Just make sure that you know the difference between the two. In terms of magnitude, it makes no difference, by the way, okay? But it would be more proper to go what is used by most of the scientists. Okay, and so speed of electron says we have, find what? It says calculate the wavelength, yeah? But by the way, there is we have something here in the frequency that is given megahertz. And how much is a mega? Mega, that would be for a million, and million would have 6 zeros, yeah, or 10 to the power 6. So once again, now I can, by the way, you can see here that I've used V as well, but you can still use C if you want to. That is wavelength times the frequency. And if we want to find the wavelength, of course, that equals to C, speed of electromagnetic waves, or you can use V, that is absolutely fine, and then divided by the frequency here. All right, in this case, the speed is 3 times 10 to the power 8. That is meter per second divided by what? If it is a radio wave, it is 88 megahertz, yeah? So 88 times 10 to the power what? Times 10 to the power 6, that would be a million. But guys, listen, if you're going to use a calculator, if it is, let's say, not the sophisticated or advanced calculator, you'll have to put this like number inside a bracket so that you get the correct answer. If not, you might get a wrong answer. So of course, once you do this, you will get 3.41 meter. Can we do the same thing for visible light? Yes, you'll just change this number. Now that was 88. Now you can use 6 here, 6 times 10 to the power 8, and here you can use, by the way, okay, let me not get confused here. We have 6 times 8 already, 6 times 10 to the power 8 already, and then we have mega as well. So you'll have to multiply by 10 to the power 6. Why? Because this power 6 is for the mega, and then this is from the number itself, let's say. So of course, 10 to the power 6 and 8, that is of course becomes 10 to the power 14, and then 6 times 10 to the power 14. Then you will put or insert this number into, or instead of this, then of course you will get the correct wavelength. And then of course we have for X-ray, here's the number, don't forget the mega, that is 10 to the power 8, so 8 and 12, that is 8 and 12, that is becomes, 6 and 12, that is becomes 10 to the power 18, yeah? Okay, because mega is 10 to the power 6, plus 12, that is 18, so 3 times 18. So you divide 3 times 10 to the power 8 divided by, let's say if I draw do the last one here, 3 times 10 to the power 12 times 10 to the power 6, yeah? And of course this is equal to 10 to the power 18, yeah? So this is very messy now. Let's move this up a little. So we can say speed equal to wavelength, which is, my bad, not this. Okay, wavelength equal to speed of light, 3 times 10 to the power 8, divided by, we said the frequency, which becomes 3 times 10 to the power 18 here, okay? Why? Because we have 6 for mega, and then 12 already, then of course we will have 18. Once you divide the two, of course, you will get 1 times 10 to the power negative 10 meter. That is the wavelength of the X-ray. By the way, do you notice this? As the frequency increases, what happens to the wavelength here? Okay, take a look. 88 megahertz. You can see that 6 times this much times the mega, all right? And then 3 times 10 to the power 12 times mega. So we can see that as the frequency increases, yes, by the way, the frequency here is increasing, right? You can see that the wavelength is decreasing. By the way, this arrow, it doesn't mean going downward or decreasing. If we start from this point to this and this, of course, the wavelength is, or the frequency is increasing, as you can see here, okay? But the wavelength will decrease. So remember we said that the relationship between frequency and wavelength is inversely proportional, because the speed of the electromagnetic wave is the same if it is in the same medium. So by increasing the frequency, the wavelength must decrease. Take a look at this one here. It says a tuning fork produces sound with a frequency of 256 Hz and a wavelength of 1.35 meter. What value does this gives to the speed of sound in the air? So let's do this. It says what? find the speed of what? The speed of sound in the air. So we know that the speed of sound in the air, frequency times wavelength. Very good. What is the frequency? 256 times, what is the wavelength? That is 1.35. And of course, once you multiply all this, you'll get the speed of sound, which is in the air, that is 346 meters per second. Very good. What about the second one here? It says, what would be the wavelength of the same sound in water in which the sound, let's say, travels at 1,500 meters per second? Now, this might become a little bit tricky here. Remember this, they are telling you or asking you to find what? To find, wait, let me get this or hide the answer first and then we can discuss this. What would be the wavelength? So find the wavelength, okay? What is the wavelength? The speed of sound is given, which is 1,500 meters per second, correct? But in order to find the wavelength, what do I need? In order to find the wavelength, I need both speed and frequency, but do I have the frequency here? The answer is no, but hey, don't forget, we said frequency never changes, okay? It doesn't matter if it is in the air or water or in any other, let's say, mediums or whatever, yeah? The frequency will always remain the same. Since it is the same sound, yeah? That means it has the same frequency. So what was the frequency in the previous part? I mean, the frequency that we have, not in the previous part, the frequency is 256 hertz, yeah? And then, of course, now you can find the wavelength, okay? So 1,500, okay? That is the speed of the wave, let's say, or sound wave, and then divided by the frequency, which is 256. Use your calculator, you will get the answer, of course, and the answer must be 5.8 meter. Okay, since it is a wavelength, it is just in meter. Okay, and I'm afraid that is all the time that we have for this session. Next session, inshallah, we'll continue solving all the remaining questions, and then, of course, then we'll move on to the next concepts. So stay with us and make sure you practice well enough. Until then, stay safe. Assalamu alaikum wa rahmatullah.